Hi, my name is Stefan Mabry, and I am a PhD student at the University of North Dakota. Today I'll be presenting on multiple linear regression, which is a powerful statistical technique that helps us understand the relationships between multiple independent variables and a dependent variable. This method is widely used in fields like healthcare, finance, and engineering to make data-driven decisions. Let's dive in. So in this project, we aim to explore the relationship between three variables, x1, x2, and y, using multiple linear regression through a custom implementation in Python. Multiple linear regression allows us to quantify how well independent variables, such as x1 and x2, can predict the dependent variable y. The primary goal is to assess the effectiveness of this predictive model by analyzing key regression metrics, such as the slopes of the regression line or the y-intercept, and then the r-squared value, which indicates how well the model fits the data. Additionally, we evaluate error metrics, including mean absolute error and root mean squared error, to gauge the accuracy of our predictions. One important challenge in regression modeling is handling variables with different scales, as we'll see in this data set. This often requires normalization techniques to ensure that no single variable disproportionately influences the model. Let's take a closer look at the implementation, where I'll quickly go over 4 parts of the code. First, I'll cover the gradient descent algorithm, which is my model, which for my model is the entirety of the code for the model building process. Then I'll cover the validation computations. For exploratory reasons, I implemented most of them. And then, and this certainly exposes my inner nerd, I'll briefly touch on some things that I think are neat in my loading code, and probably unique, or at least different than yours, as well as unit testing. And I'll talk about some of the importance of unit testing as our model and modeling code becomes more complicated. So this slide represents the core multiple linear regression model, the gradient descent function, which iteratively optimizes the model parameters, or theta values, to minimize the error in predictions. The reason why I call it theta is because of convention and not out of any sense of creativity. The function, which I call as run gradient descent, it takes in xx, which is the feature matrix containing x1 and x2, yy, which is the target variable y, and then learning rate, which controls the step size for updates, as well as iterations, which defines how many times the algorithm will refine the parameters. A quick note, like a programming note, I know that most of you are not software engineers, so the reason why I pick variables that have at least 2 letters is because when you do a control F to find them, you can find these as opposed to like just I or M, which happens to be in lots of words. Normally I would use II here and I would use MM here, but this was small enough that I didn't bother. So we start off by doing the initialization. So theta is initialized as 0 vector, and then also I initialize the MSE log file, which is this isn't a file, this is a list, but I implement it. I initialize it as empty, and the reason why I do this is because I'm running all of these in lockstep or in sequence, and so this is basically clearing out the value, because I pass it back out when I'm done, and so this is clearing it out, so that when I pass it out, it's empty, or only full of the stuff that we're going to set it for, and this allows me to have a separate log for every run, and then M is how many elements are in the target array. So then there's the iteration loop, which the function runs for the number of specified iterations that we passed in, and we set the predictions. And so this has to use matrix multiplication because we've got a multi-dimensional array that we're multiplying by. In the simple linear regression, you didn't have to do this because Python would just go through and figure out all the multiplications between element to element, whereas with a multidimensional array you need to use NumPy's matrix multiplying function. So it calculates the predictions based off of what our x's are currently and what theta is. And I'll cover that, the breakdown of what theta is in a minute. And that builds our predictions, and then we set the error, which is the predictions minus the YY value, at the same point in the matrix, and that builds a matrix of errors. And then we have the MSE, which is our error squared essentially, and then we set it to our log so we can then file it later. And then we figure out what the gradient looks like based on the error, and so that's going to tell us which direction we need to step. And eventually we won't be taking steps if we once our model converges on the answer. So then we deal with the gradient times the learning rate, which is the size of our step, and then that builds in and that updates theta with those values. So theta is when it's updated, it's got three parts. So there's theta 0, which is our y-intercept value. There's theta 1, which is the slope in the x1 dimension. And then there's theta 2, which is the slope in the x2 dimension. So this is the function that we're trying to optimize, so that when we place in x1 and x2, we're going to get a predicted y, and then that becomes our prediction. And that's what we're doing at the top of the loop here. And we also do it here. We get the y predictions, and we do the subtractions here. So once our model is converged, or we're done running the iterations, we're going to do some validation. So we evaluate, the validations go to evaluating its performance. So this slide shows the validation functions used to measure how well the regression model predicts y based on x1 and x2. So the first function I have here is r squared, and I actually like r squared a lot. I know there's a little bit of not liking it for data science, but I actually like it a lot, probably because I did science in my previous life, and this becomes the gold standard for how well your project worked in science. So this measures the proportion of variance in y that is explained by x1 and x2, and so it's calculated. I made it more complicated than it needs to be, but I do it in 2 steps. So this is the sum of the residuals. The numerator is the sum of the residuals, and then we square them, and so this is the error that you have, and then SS tot is the total variance of y, and so the higher r squared value indicates it's a better fit. And the reason why is because we take this error, right, which is that this would be normally a measure of the error, but then we're doing 1 minus it, and then that becomes then the measure of how much the x1 and x2 influence y, or explains the variance of y with x1 and x2. That sounds more confusing than it needs to be, but this measures the error, basically. We also have the mean absolute error as because r squared alone doesn't tell us the full story, so we want to use other error metrics. So here's mean absolute error, and so the average absolute difference between the predicted and actual values. This provides an easy to interpret measure of prediction accuracy. And then there's the mean squared error, which is similar to MAE, but it squares the errors before averaging them. So this gives more weight to larger errors. So if you think that larger errors or bigger errors should influence your model more, or it should be treated with more weight, then you want to use the root mean squared error. Then you want to use there's the mean absolute mean, median absolute mean absolute error. I got a mistype in here, but it's a more robust alternative to the MAE. So it uses the median instead of the mean to reduce sensitivity to outliers. And then there's the mean absolute percentage error, which is one that I like the most. And so it expresses errors as a percentage of actual values, making it useful for when the magnitude of y varies significantly. So by analyzing these metrics together, we can assess the model's accuracy and identify areas for improvement. So next I'll briefly highlight some interesting aspects of the data loading process and the unit tests that help me refine this implementation. So yeah, just briefly on the import function. So the data came in the form of an Excel with this project, and previous data came as a CSV. So instead of converting the Excel to a CSV, I just imported it as an Excel document, and I used the Python library for doing Excel loads. However, in the case that our professor decides to do the pre-processing step of converting the file to a CSV file, or maybe there's a CSV file laying around and I happen to have gotten, for some reason, the XLS version, then I also load the CSVs. But one important note is that sometimes different CSVs can be encoded differently. For example, you could have an 8-bit encoding per character for your ASCII versus a 16-bit version, right, for Unicode. And so when loading these, you should always detect, what type of encoding that the CSV has so that you load it appropriately. And so this detection function also comes from a Python library. So anyway, I found this out the hard way through unit tests, which brings us to unit testing itself. So, one thing I like to point out, and again, I know that not all of you are software engineers in your previous lives. So, when you're writing unit tests, when you're writing code that gets complicated, you want to try to create a unit test to go along with it, because a unit test has, it's a very self-contained space of data that and you know what the result is going to be. And that way, when you make a change in your code, that you can then understand how that change impacts everything, but with an apples to apples comparison every time. And this helps with finding bugs prior to you go to to a production run. And this is when I found, again, that bug with the CSV file. So I created a CSV file here, and then I created the Excel, and then I ran the two, because I loop over the collection of the two files, and then I run the same analysis with both, and then I clean it up. And when I did this loading, I ran into an error that my encoding for here was different than the encoding that I was expecting in my run. So this is what found that error, and this is how I know that we should always detect the encoding format prior to doing a load, so that you don't throw any errors. So with this class, we're getting to the point where our models are becoming more complicated, and so having unit tests will help you deliver that code faster and in a more robust way. And when you're writing code, you should always modularize it so that it all has separate functions that you're calling. That way you can write a unit test, because you can't write a unit test without that. So the results. The results of this multiple linear regression analysis, it confirms that the optimal hyperparameter configuration for this data set is the learning rate of 0.01 and 10,000 iterations. So this setup achieves the best trade-off between convergence speed and model accuracy, as we see with the R-squared, the MAE, the RMSE, the MAE, and the MAPE. And then I bolded the first iteration set that has, where the model achieved like its full final convergence. So with lower learning rates, such as 0.001, 0.0001, 3 zeros, and then 4 zeros, and then 1. So with these lower rates, these initially struggled, even to the point of having a negative r squared value, which means that so this means that the prediction of this model at this point in time is less predictive than just taking the mean of the space. So it's actually worse than doing nothing, which I found that amusing. So yeah, as we increase them, they eventually all converge at the same values. So at that point, you should always take the more performance, the performance friendly version, so that you're not wasting CPU cycles. So yeah, the MAPE remains relatively consistent between these. So that means that they have, this indicates that the errors are distributed evenly across the data set. They don't improve meaningfully with any additional iterations. And then the fact that everything gets to the same point eventually means that iterations is not a good measure of, or not a good hyperparameter to tune when you're trying to improve the model's performance. So for feature scaling, I used the z-score normalization rather than the max normalization technique that we learned in class. So z-score normalization, it standardizes the data to have a mean of 0 and a standard deviation of 1, making it a more robust normalization technique for like more extreme values. It also preserves negativity, which max normalization does not. And so max normalization, it puts all the values between 0 and 1. So then, that can be highly sensitive to outliers, which can distort, learning models, and then features that have like large variances, which, I feel like this one does have a large variance. So yeah, given these findings, future improvements, in this model, they shouldn't focus on increasing iterations, but rather a feature selection, a better feature selection, or polynomial expansion or alternative regression techniques like lasso or ridge regression to enhance the model's performance further. But with these results in mind, I'll show you some charts. So here are the error bars that we recorded for the recorded versus the predicted values. This chart looks exactly like our examples. I'm guessing that the data from our example is the same that we used in this project. But it does look really pretty. And then, here's the comparison between runs for the MSE convergence. They all go to about the same point. You can see that these lines look basically the same. The one thing that is different between them, though, is the number of iterations. So, the 0.01 is it's going through the iterations faster, right? And it converges around the 5,000 mark. And then the same thing goes for the 0.00001. So this is the slowest learning rate, and it does learn slower. And at the 10 million iterations mark is the one that finally converged, and it converged really around the 5 million iterations mark when you look at the logs. So this is normally there we go. So this is normally where I'd say like ask for some questions, but you can reach out to me because we're digital. So you can reach out to me at my email address, or you can visit me in Madison if you happen to be in the area. We can go hang out, and or you can reach out to me on LinkedIn, and that's always a good place to get a LinkedIn and connection. Well, thank you, and thank you for watching this presentation, and have a good day.